Welcome! In this session, we'll explore the problem titled Vowel Spellchecker.
This coding problem challenges us to create a spellchecker that is robust and handles queries in a flexible way by leveraging case insensitivity and vowel replacement rules. Let's dive in to understand the problem and solve it step by step. In this problem, we need to create a spellchecker that takes in two inputs, a word list and a set of queries. The word list consists of unique words, and our job is to check each query against this word list using a series of rules. First, we perform an exact match, where the query must match a word in the word list exactly, including case sensitivity. If no exact match is found, we move to a case-insensitive match. Here, if the query matches a word in the word list when case is ignored, we return the first such match. If there is still no match, we apply the vowel error rule. In this rule, vowels in the query are replaced with a special character, represented as asterisk. For example, the word hello becomes H*LL*. We then compare this transformed query to the word list, where vowels in the word list are also replaced with asterisk. If a match is found, we return the first such match. Finally, if none of these rules produce a match, we return an empty string for that query. Each query is processed in the order it appears in the queries list. The output for this problem is a list of strings, where each element corresponds to the result of spellchecking a query in the queries list. To understand this better, let's look at an example. Suppose the word list contains the words kite, kite, hair, and the queries list contains words like kite, hair, here, ketty, keet, and keto. The output for this input is a list where the first query, kite, matches exactly with kite in the word list. The second query, kite, doesn't match exactly but does match kite when case is ignored, so kite is returned. Similarly, kite matches exactly, and hair matches exactly as well. For hair, there's no exact match, but a case-insensitive match is found with hair. For the next few queries, the results depend on the vowel error rule. Here and here fail both exact and case-insensitive matching, so we apply the vowel error transformation. When vowels are replaced with asterisk, here becomes H*R, but this does not match any word in the word list. As a result, an empty string is returned for both queries. Next, ketty also fails exact and case-insensitive matching, but its vowel error form matches kite, so kite is returned. For keet, no match is found even after applying the vowel error rule, so an empty string is returned. Finally, keto matches kite through the vowel error transformation. This example shows how the spellchecker prioritizes exact matches first, followed by case-insensitive matches, and then vowel error matches, while returning empty strings for queries that fail to match any word. Let's look at another example to further clarify. If the word list contains apple, orange, and banana, and the queries list includes apple, orange, banana, EPPL, banana, and O**ange, the output is a list where apple matches apple when case is ignored, so apple is returned. Similarly, orange matches orange, and banana matches banana, both through case-insensitive matching. For APPL, there is no exact or case-insensitive match, nor does it yield a valid match through vowel error transformation, so an empty string is returned. For banana, a case-insensitive match with banana is found, so banana is returned. Lastly, O**ange does not match any word in the word list under any rule, so an empty string is returned. This example highlights the importance of correctly handling case-insensitive and vowel error transformations to ensure accurate results. Now, let's consider some additional constraints and edge cases. The words in both the word list and queries are composed only of English letters, and their lengths range between 1 and 20 characters. The size of the word list in queries is at most 10,000, meaning that our solution must be efficient to handle these upper bounds. Edge cases to keep in mind include scenarios where the queries list is empty, in which case the output should simply be an empty list. Additionally, if none of the words in the queries list match any word in the word list, even after applying the vowel error rule, the output should consist of empty strings for all such queries. Another important case is when identical words with different cases are present in the word list. The spellchecker must adhere to the order of words in the word list when resolving case-insensitive and vowel error matches. Finally, for large inputs, it is crucial that our approach is optimized to handle the maximum input size efficiently.
To begin tackling this problem, we first consider a brute force approach.
The intuition here is fairly simple. For each query in our list, we compare it against every word in the word list using 3 matching rules. First, we look for an exact match, which involves directly comparing the query with each word. Next, we address case-insensitive matches by converting both the query and the words in the word list to lowercase before comparing. Finally, we handle vowel error matches by replacing all vowels in both the query and the word list words with a placeholder, such as an asterisk, and then comparing these transformed versions. While this method is straightforward and easy to implement, its performance is poor due to the repeated string comparisons and transformations. With n queries and m words in the word list, the time complexity becomes O, n asterisk m asterisk k, where k represents the average length of the words. This makes it inefficient for larger inputs, prompting us to explore a more optimized solution. An optimized approach leverages hash maps to improve the efficiency of our solution. The idea is to pre-process the word list into 3 dictionaries, each targeting a specific type of match. First, we create an exact match dictionary, where the original words from the word list are used as keys for direct lookup. Second, we construct a case-insensitive dictionary by storing the lowercase version of each word as the key and mapping it to its original form. This allows us to quickly find matches without worrying about capitalization. Lastly, we build a vowel error dictionary by transforming words to replace all vowels with a placeholder, like an asterisk, and using these transformed words as keys that map to their original forms. During query processing, we follow a clear hierarchy: start by checking for an exact match in the original dictionary, then look for a case-insensitive match, and finally, attempt a vowel error match using the last dictionary. If none of these checks yield a result, we return an empty string. This approach significantly enhances performance, as pre-processing the word list takes O, m asterisk k, time, and querying takes O, n asterisk k. Combining these, the total time complexity is reduced to O, m asterisk k plus n asterisk k, which is much faster than brute force for larger datasets. Another approach we could consider is using a tree, or prefix tree, to store the word list for efficient matching. A tree organizes words in a tree-like structure, where each node represents a character. To handle case-insensitive matching and vowel substitution, we could enhance the tree with additional flags or transformations at each node. However, while this method can reduce pre-processing time slightly, it introduces complexities in both implementation and maintenance. Additionally, tries tend to use more memory compared to hash maps, especially when storing transformations like vowel replacements. After evaluating these options, we chose the hash map approach as the most practical strategy. It strikes a balance between performance and implementation simplicity. By pre-computing dictionaries, we not only ensure fast lookups but also align with the problem's requirements effectively. A key insight here is the hierarchy of matching rules. Exact matches take precedence over case-insensitive matches, which in turn take precedence over vowel error matches. Structuring our dictionaries in this way allows us to process queries efficiently. Another pivotal realization was that transforming words by replacing vowels with a placeholder greatly simplifies the vowel error matching process, making the implementation cleaner and more efficient overall. By adopting the hash map approach, we achieve a solution that is both highly efficient and manageable in complexity. This method minimizes repetitive string comparisons while keeping the implementation straightforward. The pre-processing step ensures that querying is optimized, making it the most practical choice for this problem. While alternatives like brute force and tries were considered, hash maps provided the best trade-off between speed, simplicity, and memory usage. Overall, this approach not only handles the required matching rules effectively but also scales well for larger inputs, making it the ideal strategy to solve the vowel spellchecker problem. To solve the vowel spellchecker problem, we need to design an algorithm that can efficiently match queries to the most appropriate word in the provided word list. The matching follows a specific hierarchy of rules. First, if a query exactly matches a word in the word list, we return that word. Second, if there's no exact match, we check for a case-insensitive match, or we ignore capitalization differences. Third, if neither of those matches is found, we allow for vowel errors by treating all vowels a, e, I, o, u as interchangeable and attempt a match. If none of these rules apply, we simply return an empty string for that query. To implement this efficiently, we pre-process the word list by creating 3 dictionaries. The exact match dictionary allows direct lookups for exact matches. The case-insensitive dictionary maps each lowercase word to the first occurrence of that word in the word list, enabling quick case-insensitive checks. Finally, the vowel error dictionary transforms words by replacing vowels with a placeholder character, such as asterisk, simplifying the handling of vowel mismatches. These pre-processing steps lay the groundwork for efficiently checking queries against the word list. To handle vowel errors effectively in our algorithm, we need a helper function that standardizes words by replacing all vowels with a placeholder, such as asterisk. This ensures that words with different vowel combinations can be matched consistently. Once this function is in place, we move on to processing each query. For every query, we follow a systematic approach. First, we check if the query has an exact match in the exact match dictionary. If no exact match is found, we convert the query to lowercase and look it up in the case-insensitive dictionary. If this also fails, we replace the vowels in the query with asterisk and check the vowel error dictionary. If none of these checks yield a result, we return an empty string for that query. Finally, we collect the results for all queries and return them as a list, ensuring that each query is resolved as efficiently as possible. By organizing our algorithm this way, we ensure clarity and speed in handling the different matching rules. The vowel error dictionary is a crucial part of our pre-processing since it allows us to handle vowel mismatches efficiently. By replacing all vowels in a word with asterisk, we can standardize words that differ only in their vowel usage. This transformation simplifies the comparison process during query resolution. Pre-computing these dictionaries not only enables fast lookups but also ensures that the algorithm adheres to the hierarchy of matching rules. We always prioritize exact matches first, followed by case-insensitive matches, and finally vowel error matches, ensuring that the most specific conditions are applied before more generalized ones. The pre-processing phase involves building the exact match dictionary in O(n) time, where n is the number of words in the word list. The case-insensitive dictionary also takes O(n), while constructing the vowel error dictionary takes O(n*)m, where m is the average word length. When processing the queries, each lookup involves 3 O(1) dictionary checks, leading to a per-query complexity of O(m). For Q queries, the total time complexity is O(q*m). This pre-processing approach ensures the algorithm is both time-efficient and scalable. When implementing this algorithm, it's important to consider edge cases to ensure robustness. For example, we need to handle queries that have no matches in the word list or in any of the dictionaries. Similarly, we should account for cases where multiple words in the word list are case-insensitively identical to the query. Our algorithm must consistently return the first occurrence. Queries with multiple vowel errors also need careful handling to ensure the vowel error dictionary functions as intended. Additionally, if the word list or queries are empty, the algorithm must handle this gracefully without errors. Let's look at an example to illustrate the algorithm. If the word list is kite, kite, hare, hare, and the queries include kite, 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 hare, hare, here, here, ketty, keet, keto, the output should be kite, 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 hare, hare, comma, kite, kite. This example demonstrates how the algorithm resolves queries based on the hierarchy of rules. In the example, kite matches exactly with itself in the word list, so it's returned directly. Kite, although not an exact match, matches case-insensitively with kite, so kite is returned. Similarly, hare matches exactly, while hare is resolved case-insensitively to the first occurrence of hare. However, here and here do not match any word in the word list, even after considering vowel errors, so empty strings are returned for these queries. Ketty matches a vowel error transformation of kite, so kite is returned. On the other hand, keet has no match, resulting in an empty string, and keto also matches a vowel error transformation of kite, returning kite again. This walkthrough highlights how the algorithm systematically applies the matching rules in their defined order to resolve queries effectively. By leveraging pre-processing and efficient lookups, the algorithm handles even complex cases with consistency and speed. This solution addresses LeetCode problem number 966, Vowel Spellchecker. The solution involves matching queries against a given word list based on 3 increasingly lenient rules: exact matches, case-insensitive matches, and vowel-insensitive matches. The first step is defining a helper function to vowel to replace vowels a, e, I, o, u with a placeholder character asterisk. This function is used to implement vowel-insensitive matching. Next, we initialize three data structures to store exact, case-insensitive, and vowel-insensitive word mappings. The exact_word set stores all words in the word list for quick exact matching using constant time lookups. The case_insensitive dictionary maps lowercase versions of words to their original forms. This allows retrieval of the first word from the word list that matches a query ignoring case. Lastly, the vowel_insensitive dictionary maps vowel-removed versions of lowercase words to their original forms, enabling vowel-insensitive matching.
We populate these dictionaries by iterating over the word list.
The setDefault method ensures that the first word encountered for a given lowercase or vowel-removed representation is stored.
For each query, we check the three matching rules in order of priority.
If the query exists in the exact_word set, it is added directly to the result.
If not, we lowercase the query and check the case_insensitive dictionary.
Finally, if no match is found, we apply the devowel function to the lowercase query and check the vowel_insensitive dictionary. If no match exists even after these steps, we append an empty string. This approach efficiently handles the problem requirements with preprocessing to enable fast query lookups. The overall complexity is proportional to the size of the word list plus the number of queries, making it suitable for large inputs within the given constraints.
To implement the Vowel Spellchecker in Java, we start by importing the necessary packages and defining our main class and method.
The method, Spellchecker, takes two inputs, the word list, which contains valid words, and queries, which are the words we need to check. Inside this method, we define a helper function called devowel. This function replaces all vowels in a given word with an asterisk, making it easier to perform vowel-insensitive matching later. It iterates through each character of the word, checking if it's a vowel, and appends either an asterisk or the character itself to a string builder.
The processed word is returned as a string.
Next, we establish three data structures to handle different types of word matches. The exact word set stores all words from the word list for exact matches. The case-insensitive map associates a word's lowercase version as the key and the original word as the value, enabling case-insensitive matching. Similarly, the vowel-insensitive map uses the devowel function to create keys where vowels are replaced with asterisks, making vowel-insensitive matching possible.
The putIfAbsent method ensures that the first occurrence of a key-value pair is retained without overwriting. By iterating over each word in the word list, we populate these collections for efficient lookups.
After building the collections, we initialize an array called result to store the output for each query. We then loop through the query's array, processing each query one at a time. First, we check if the query exists in the exact word set for an exact match, and if it does, we assign it directly to the result array. If the exact match fails, we attempt a case-insensitive match by converting the query to lowercase and checking the case-insensitive map. If a match is found, the corresponding word from the word list is added to the result.
When both the exact and case-insensitive matches fail, we perform a vowel-insensitive match. Here, we use the devowel function on the lowercase version of the query and look it up in the vowel-insensitive map.
If a match exists, we retrieve the word. Otherwise, we default to an empty string for unmatched queries. Finally, the method returns the populated result array, which contains the best matches for each query based on the given rules. To solve the Vowel Spellchecker problem, we start by preparing our input data. First, we define a helper function called devowel, which replaces all vowels e, I, o, and u with a wildcard character asterisk. This will help us handle vowel-insensitive comparisons later. Next, we initialize three key data structures. The first is exact_words, which is a set containing all the words in the word list exactly as they are. For this example, it starts with kite, kite, hair, hair. The second structure is case_insensitive, a dictionary that maps lowercase versions of each word to their original form. Initially, this dictionary is empty. The third structure is vowel_insensitive, another dictionary, which maps vowel-removed lowercase versions of words to their original forms, and it also starts out empty. These structures will provide the foundation for the three levels of matching: exact, case-insensitive, and vowel-insensitive. Now, we process the word list to populate the case_insensitive and vowel_insensitive dictionaries. For the first word, kite, we convert it to lowercase, resulting in kite, and apply the devowel function, producing k*t*. We then update case_insensitive to map the lowercase kite to the original kite and update vowel_insensitive to map k*t* to kite.
Next, we process the word kite. Its lowercase version is also kite, and its devowel representation is again k*t*. Since case_insensitive and vowel_insensitive already contain these mappings, no updates are needed. We repeat this process for the remaining words, hair and hair. After processing all words, case_insensitive maps kite to kite and hair to hair, while vowel_insensitive maps k*t* to kite and h*r* to hair. These mappings allow us to handle case and vowel-insensitive queries efficiently. Next, we process the queries to determine their matches based on our three data structures. The first query is kite. Since it is an exact match in exact_words, we add kite to the result. For the second query, kite, there is no exact match in exact_words, but it matches in case_insensitive, so we add the corresponding original form, kite, to the result. The third query, kite, is an exact match again, so we add kite to the result. Finally, for kite, there is no exact match, but it matches in case_insensitive as kite, so we add kite to the result. The final output for this example is kite, 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 demonstrating how the solution handles exact and case-insensitive matches effectively. Now we look at an example that highlights vowel-insensitive matching. The word list remains the same, and the queries include words like hair, hair, h_e, and h_e. We begin with the same pre-processing steps to initialize exact_words, case_insensitive, and vowel_insensitive. For the first query, hair, we find an exact match in exact_words, so we add hair to the result. For hair, there is no exact match, but it matches in case_insensitive, so we add hair to the result. The third query, h_e, does not match in exact_words or case_insensitive, but its vowel-insensitive form, h*r*, matches in vowel_insensitive, so we add hair to the result. The same reasoning applies to h_e, which also maps to h*r*. The final output for this example is hair, 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 showcasing the effectiveness of vowel-insensitive matching. Finally, we consider an example where none of the queries match. The word list remains the same, but the queries are hello, world, and test. As before, we pre-process the word list to initialize exact_words, case_insensitive, and vowel_insensitive. For each query, we check against all three data structures. None of the queries have an exact match in exact_words, a case-insensitive match in case_insensitive, or a vowel-insensitive match in vowel_insensitive. Since no matches are found, the result for each query is an empty string. The final output is, which illustrates how the solution handles cases with no matches across all levels of comparison. Here, we start by discussing the time complexity of the pre-processing step, where we construct the dictionaries needed for efficient query resolution. If n is the number of words in the word list and l is the average length of these words, the operations for each word include converting it to lowercase, which takes O, L, and creating its devowel version, which also takes O, L. Inserting these transformed versions into the dictionaries, case_insensitive and vowel_insensitive, is an O1 operation on average, thanks to hash table efficiency. Since these steps are performed for all n words, the total pre-processing time is O(n*L). This pre-processing ensures that we can handle queries efficiently later on, leveraging these dictionaries for quick lookups. Now, let's shift to the time complexity of the query processing step. If m is the number of queries and k is the average length of these queries, each query requires several operations. First, checking for an exact match in the exact_words set is an O1 operation. Then, converting the query to lowercase and checking it against the case_insensitive dictionary also requires OK for the transformation and O1 for the lookup. Similarly, creating the devowel version of the query and looking it up in the vowel_insensitive dictionary involves OK and O1, respectively. Combining these, each query takes OK for transformations and O1 for lookups, leading to a total query processing time of O(m*k) for all queries.
When we combine this with the pre-processing step, the overall time complexity becomes O, n*L plus m*K, where pre-processing and querying contribute independently.
Next, we consider the space complexity.
For the pre-processing step, we store the original words in the exact underscore words set, which takes O, n*L, space because it stores all n words with their average length L. Similarly, the case underscore insensitive dictionary maps lowercase representations of words to their original versions, also requiring O, n*L. The vowel underscore insensitive dictionary, which maps devoweled lowercase words to their originals, has the same space requirement. Thus, the total space required for these dictionaries is O, n*L. During query processing, temporary storage is needed for transformations, such as the lowercase and devoweled versions of a query. Since each query is processed individually, this space requirement is O, K, per query. Adding these together, the overall space complexity is O, n*L, dominated by the storage of dictionaries, with O, K, as a minor addition for query transformations.
To put this into perspective, we compare the current optimized approach with a naive solution.
In the naive approach, each query is compared against all words in the word list, performing 3 checks: exact match, case-insensitive match, and vowel-insensitive match. This results in a time complexity of O, m*N*L, as every query involves transformations and comparisons against n words, with each transformation taking O, L. However, this approach requires no additional data structures, so its space complexity is O, 1. In contrast, the optimized approach pre-processes the word list into dictionaries, enabling O, 1 lookups for each query. This reduces the query time complexity to O, m*K, resulting in an overall time complexity of O, n*L plus m*K. The trade-off is an increased space complexity of O, n*L, due to the dictionaries. This optimization is especially valuable for large inputs, where the naive approach becomes computationally expensive. Finally, let's analyze the best, average, and worst-case scenarios for the optimized approach. In the best case, all queries are exact matches. Since this only involves O, 1 lookups in the exact underscore words set, the time complexity is O, n*L plus m, where pre-processing remains the dominant factor. In the average case, queries require transformations and lookups in multiple dictionaries, resulting in a time complexity of O, n*L plus m*K. In the worst case, every query involves devoweled transformations and lookups, but the time complexity remains O, n*L plus m*K, since the query processing step is consistently bounded by O, K. Overall, the optimized approach demonstrates a significant reduction in query time complexity by leveraging additional space, making it highly effective for scenarios with large word lists and queries. In tackling the vowel spellchecker problem, there are some common mistakes to watch out for. First, overlooking edge cases can cause significant issues. For example, not handling empty inputs, such as an empty word list or query, or failing to consider special characters in words, can result in runtime errors. Always account for scenarios like empty strings, case sensitivity, and unexpected characters. Another frequent mistake is using inefficient matching strategies. A brute force approach that directly compares each query to every word in the word list has a time complexity of O, n*M, where n is the length of the word list and m is the number of queries. This can quickly lead to timeouts for large inputs. Additionally, misunderstanding how to handle case insensitivity can create errors. While converting all words in queries to lowercase is a step in the right direction, the transformation must be applied consistently throughout the solution. Lastly, ignoring problem constraints can lead to overly complicated solutions. For example, if word lengths are relatively small, pre-processing the word list with a hash map could significantly speed up searches and simplify the implementation. Now, another important consideration is ensuring the correct priority in matching rules. When a problem specifies multiple matching rules, such as exact match, case-insensitive match, or character substitution, those rules often need to be applied in a strict order. Skipping this prioritization or applying the rules in the wrong sequence can lead to incorrect results. Shifting focus to interview settings, pre-processing plays a critical role in many string matching problems. For instance, you can pre-process the word list into efficient data structures like hash maps, tries, or sets. Hash maps, for example, are particularly effective for storing lowercase versions of words to facilitate case-insensitive matching. However, pre-processing comes with trade-offs. While it increases upfront time and space complexity, it often reduces the average query time substantially. Highlighting these trade-offs and discussing them with your interviewer demonstrates a deeper understanding of algorithmic design. Additionally, always communicate your assumptions clearly, especially in problems involving fuzzy matching, such as handling wildcards or typos. Misaligned expectations can lead to implementing the wrong solution. Finally, scalability is key when working with large inputs, like a word list containing hundreds of thousands of words. In such cases, brute force methods are rarely acceptable. Instead, consider more efficient techniques, such as tree-based searches or leveraging hash maps, to reduce computational complexity. To deepen your understanding of related concepts, you might explore similar problems on LeetCode. Examples include Vowel Spellchecker, group anagrams, find and replace pattern, and replace words. These problems share overlapping techniques and can provide additional practice with string manipulation and matching rules. As for alternative approaches to solving the Vowel Spellchecker problem, hash map pre-processing is a popular choice. By creating a hash map with transformed keys, such as lowercase or vowel-removed versions of the words, you can achieve constant-time query lookups at the cost of O(n) space for pre-processing. Another option is to use a tree, which enables fast prefix-based or fuzzy matching. While tries can reduce memory usage for common prefixes, they are more complex to implement. Sorting the word list and using binary search is also viable for exact or near-exact matches, though it's less suitable for problems requiring fuzzy matching. Lastly, brute force is the simplest approach to implement and works well for small input sizes but becomes computationally expensive for larger datasets. Choosing the right approach depends on the problem constraints, input size, and the specific trade-offs you're willing to make between time, space, and implementation complexity. Great job! To wrap up, we reviewed the Vowel Spellchecker problem and discussed the efficient use of hash maps for pre-processing and querying. Remember to practice similar problems to sharpen your skills. Thank you for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!